Hello everyone, welcome to the 13th session of quantum field theory. Today we are going to talk about Wick's theorem, which are the basic ingredient for Feynman diagram calculation. So the point of this theorem is to break down the endpoint correlation function to two-point correlation function. So as you're going to see, it's called contraction. So in general, when you want to calculate the time-ordered expectation value of endpoint correlation of a field, which here you can see the notation, phi 1 means phi of x1, phi n means phi at point xn. The whole point of this theorem is to how to break it into the two-point correlation functions, which we know how to calculate it for the free fields based on creation and annihilation. And this is a very useful theorem in order to be able to calculate the Feynman diagram. So we start from the case of n equal to 2. So we have the two-point correlation function. So the conventional notation is that by considering the causality, you have these Heaviside functions, and these Heaviside functions are just ordering which time is happening after the other one. So any field, again, consider something like Klein-Gordon field. I'm using the index I, can be decomposed into something that we call it positive frequency and negative frequency. Okay, and so the whole point is that the positive frequency for the free field does have a p, or annihilation operator. Or you can put a minus here, and the negative frequency is the opposite. Same kind of coefficient here, but you have a dagger p of ip.x. And the whole point is that if you have the positive frequency on vacuum, you're going to have 0. And if you have a negative frequency on a vacuum on the other side, that's also equal to 0. So we use that in order to reorder the multiplication of two fields. So imagine I'm considering again like two fields, phi of x, phi of y, instead of x1 and x2. So x1 is x and x2 is y. So imagine a case that x0 is larger than y0. So x0 happens after y0. So this is going to be phi x, phi y, right? So we want to calculate this expectation value. Well, let's decompose these two fields into the positive and negative frequency. So the positive frequency, so we're going to put two vacuums on the two sides, and then inside we're going to have phi x positive, phi y positive, right? Phi x positive, phi y negative, plus phi x negative, phi y positive, plus phi x negative, phi y negative. Okay, so now what's the point of this? The point of this is that all of these expectation values that have positive on the right side and a negative on the left side are going to be 0. So including this one, first one, and then this one, and this one. Okay, so they are going to be 0, and the only term which is surviving is the one in the box. But the one in the box can be, and then so this one, phi x positive and phi y negative, can be re-expressed in this way. So it can be phi x positive, phi y negative in commutation, plus phi y on the left side and phi x on the right side. So now if you replace that, you're going to have the first term is the first term. Now this is going to be phi minus negative, phi x plus phi y, phi x negative, phi y positive, plus phi x, phi minus y, plus a term in the commutator. Okay, so now what's the point of that? So the point of having that is that all of these terms are going to be 0, and then we're only going to have this term. So that is called normal ordering. So you order these fields in a way that the positives on the right side and the negatives on the left side, so that they would just make 0. So then you get rid of them, and then you're only dealing with those contraction. So this is called contraction or commutation, and the first term are somehow normal order. So the operation normal ordering on certain kind of fields with creation and annihilation operator, for example, you have AP, A dagger K, A Q. Imagine you have something like that. This is defined, so that's why I'm using 3 lines, is defined in this way. So it's going to be A dagger K, and then you have AP and AQ. And since AP and AQ, they commute with each other, so you can also interchange the order of them. So it doesn't really matter. So the whole point is that it's going to put the annihilation on the left side, and the creation on the left side and annihilation on the right side. It's called normal ordering. So this is what we do on the above. So we basically normal ordered these fields. This commutation phi plus x and phi minus y is Feynman propagator, right? Again, why is it the case? Because this is going to be phi plus x, phi minus y, minus phi minus y, phi plus x. So that's like 2 kind of propagation with causally ordered, and then you subtract them. We already defined that is the Feynman propagator. So now it's time to express this theorem. So it says the time ordered of this 2-point correlation, is going to be normal ordered of phi x and phi y. This is what we do. So we multiply the 2 fields, and then we normal ordered them, plus this df of x minus y. So the whole point is that this df of x minus y can be written in the way of phi x, phi y, with this line connecting to them. It's called contraction. So what is the meaning of contraction? Contraction of two fields is going to be, so it's going to be phi, the commutation of phi plus the positive frequency in the case that x0 is greater than y0, or it's going to be phi plus of y and phi minus of x in the case of x0 is smaller than y0. So this is called the contraction of two fields. It's just the notation. So now the time ordered of the two field or 2-point correlator is going to be the normal order of the two field multiplied plus all possible contraction. So for the case of two field, it's going to be like that. So now let's try it for the case of m equal to 4, right? So the expectation value of time ordered of phi 1, phi 2, phi 3, phi 4 is going to be the normal ordering of phi 1, phi 2, phi 3, phi 4 plus all possible contractions. So we're going to consider the cases that there are only one contraction. So you're going to have phi 1, phi 2, phi 3, phi 4. Sorry, I need to delete this. Plus phi 1, phi 2, phi 3, phi 4. Now this time phi 1 and phi 3. And now phi 1, phi 2, phi 4. Now phi 1 and phi 4 plus. Now phi 1, phi 2, phi 3, phi 4, 2 and 3, phi 1, phi 2, phi 3, and phi 4, 2 and 4, plus phi 1, phi 2, phi 3, phi 4, 3 and 4. Now you're going to have two contraction, phi 1, phi 2, phi 3, phi 4, 1 and 2, 3 and 4, phi 1, phi 2, 1 and 3, 2 and 4. 3, 5, 4. Now you're going to have 2 and 4, 3 and 1, and you are going to have phi 1, phi 2, phi 3, phi 4, 1 and 4, and 2 and 3, right? So this normal ordering is a linear term, so it can go inside of each term. So it's a linear operation, right? We can easily prove that now you can have normal ordering of each term. And the whole point is that now you say normal ordering of phi 1, phi 2, phi 3, and phi 4 on the expectation value of that is going to be 0, right? So this term, the first term here, is going to be 0. What about this term? So what is the meaning of normal ordering of, let's say, phi 1, phi 2, phi 3, phi 4? So this term is like df of x1, x2. So you're going to have normal ordering of df of x1 minus x2, phi 3, phi 4. Because Feynman propagator is already normal order, it's going to come out. So you're going to be df of x1 minus x2, now normal ordering of phi 3, phi 4. This is the meaning of the normal ordering of phi 1, phi 2, phi 3, phi 4. And this term also doesn't survive because basically this part is already the expectation value of phi of x, phi plus x1, phi of x2 minus. Now you're going to have the expectation value of this, because this is already a number, so this term is going to be 0. So these terms also doesn't, these terms also don't survive. This doesn't survive, this doesn't survive, doesn't survive, doesn't survive. So the only ones that are surviving are these 4 terms, these 5 terms here. Sorry, this one is also not surviving. So you only have 4 terms here. Sorry, I just made a mistake. One of them is actually extra. Yeah, one of them is actually, no, there shouldn't be like 4 terms. Yeah, this one, and yeah, this one are the same. Sorry, just made a mistake. Just one of them. So the only terms that are going to survive is normal ordering of phi 1, phi 2, phi 3, phi 4. So 1 and 2, 3 and 4. Phi 1, phi 2, phi 3, phi 4, 1 and 3, 2 and 4. Plus phi 1, phi 2, phi 3, phi 4, 1 and 4, 2 and 3. Yes, these are only 3 terms here. So now what's the meaning of normal ordering of phi 1, phi 2, phi 3, phi 4? It means just the multiplication of 2 Feynman propagators. So we can say to calculate a time order of phi 1, phi 2, phi 3, and phi 4, the only term that are going to survive is normal ordering of the contraction of the 2 by 2 cases. Which is going to be okay. Now, this is how we calculated 4 points correlation function. And we broke it into 2-point correlation functions, which are Feynman propagators. This we know how to calculate in the free field case. So now you can prove by the use of mathematics that if it's correct for the case of n, if it is correct for the case of n, for n plus 1 is also correct. And you can generalize. Now we get to the point of Feynman diagrams. The Feynman diagram is saying that now for the case of 4, you're going to have this x1 minus x3, x2, x4 plus so what's the meaning of each term? So imagine there are 4 points here. x1, x2, x3, and x4. So the first term is saying that there is a propagation from x1 to x2 and a propagation from x3 to x4. Now, propagation from x1 to x3. This is how we x1, x3, x2, x4 plus x1 to x4. So this is how can we distinguish them, and x2 and x3. So what's the meaning of this? Is going to say that if we have basically if we have 4 points in space-time, there are 3 possibilities that motion can happen. That there is an independent motion from x1 to x2, x3 to x4, plus the possibility of this, plus the possibility of that. And this is how you encode these correlation functions into Feynman diagrams, all possible contractions. So I mean, these diagrams are just basically each of these. So if when you say x1 to x2 and you connect it, that is equal to some number that you would call it the probability of propagation from one point to another. So I mean, these Feynman diagrams are just visualization, but each of these terms are convoluted into a number, a probability, amplitude. Okay, now let's back to the idea that we wanted to calculate. We wanted to calculate the perturbative fields, not the free field. So what we previously mentioned about the Wick's theorem was about free fields, and free fields, you can normal order them without the problem. In the previous session, we said that if instead of having free vacuum, we're going to have the interactive vacuum, and you want to calculate the time ordered now between the 2-point correlator of the interacting field, you're going to calculate a limit like that. So the limit of t goes to infinity, but in the form of I minus I epsilon of, now we write down everything in terms of free fields. So it's a time ordered of, now you had the interactive field or free field of phi x, an interactive field phi y, and then you have this exponential of minus I minus t to plus t. Maybe I expand that from dt, the interactive Hamiltonian, as a function of t, of a free vacuum. And then in the denominator, you had the normalization, very similar to partition function. Okay, so this is what we wanted to calculate. So now let's put our focus on this entity, on the nominator, and then we're going to go back to the denominator. So the denominator is going to be the vacuum expectation time ordered. Now you have this exponential that we talked about how to expand that exponential as a Dyson series of the polynomial of the 2-point correlator and the interactive Hamiltonian. So, for example, this is going to be phi of x, phi of y. I'm going to put the index I to know this is interaction, plus phi x, phi y. Now this is up to the first order. We're going to have minus I dt hi t plus the other terms of 0. Okay, so this is how we open this term here. So this is up to the first order. So the first term is going to be the 2-point correlator that we just talked about it. The Feynman diagram propagator. The second term is going to be phi I of x, phi I of y. Okay, we're going to have this term. And we previously said that one very simple form of Hamiltonian for the scalar field is going to be lambda over 4 phi 4. Okay, so we're going to have something like this. Minus I dt. Maybe now instead of t, I'm going to use z, dz. That's a different variable, but t, I'm going to replace t with z because we have x, y, and the next one that comes after that is z. So we're going to have dz phi of z, phi of z, phi of z, phi of z. I open it up because I want to use that Wick's theorem here. I'm going to put all of it in there. So I also have this lambda over 4 factorial. Maybe I put an I here. There is also an I for conventional reason. So I'm going to have the time order of phi x, phi y, interacting field. Then I'm going to have minus I lambda over 4 factorial and d4z. Sorry, maybe I should have d4z. Phi z, phi z, phi z, phi z. Now I'm going to rewrite it like this. So time ordering is on its place, and I'm going to take these two inside of this integral, okay? Because x and y are different variables. So I'm going to have minus I lambda 4 factorial. This can come out in general because this is just a coefficient. And then I'm going to have an integral. Now maybe I can write down d4z to 1 dt and d3z. Maybe this can be a notation. But at this point, I'm just going to leave it. Maybe I'm going to say d4z, right? Phi x, phi y, phi z, phi z, phi z, phi z. Okay? And now all of these fields are basically free. So I can use Wick's theorem right here. So we have 6 fields here, and 4 of them are identical. So that's going to help. And 2 of them are different because z is another point, x and y are distinguished point. Which one is going to survive? So now we are going to use Wick's theorem. The only terms that are going to survive that are made from 2 by 2 contraction. So one possible contraction is that x and y contract with each other. And then I'm going to have these 2 by 2 z terms. So first one and the last one. But if you pay attention, there are other possibilities that I'm going to show with different colors. This one and this one, imagine. But they're all the same because the z term is identical. And there is also another one, which is the first and the last, and the second and the third together. So these are like 3 scenarios that are similar. So this can be then written as, so I'm going to say there are 3 of minus I lambda over 4 factorial. Now, this term is going to be df of x minus y. And then I'm going to have the integral these operators are all linear, so integral in between is going to be preserved. D for z. Then I'm going to have df of z minus z and df of z minus z. Plus, now what are we going to have? What are we going to have? We're going to have now contraction between one x and one z and y and z. Right? So let me probably clean up this area. Now you're going to have a term that one x is contracting with z and y is contracting with z, and then there is a contraction between 2z. So 2z are free. So how many possibilities do we have? So we're going to have 4 possibilities for the first one. So if x want to contract with one of those, it's going to be 4. And then the remaining y is only have 3 choices. So 4 times 3 is equal to 12. So you're going to have 12 of minus omega over 4 factorial integral d for z. Now you have df of x minus z, df of y minus z, and df of z minus z. So this is going to be up to the first term, the time ordered of phi x, phi y integral of minus I 4 factorial d for z of phi 4 of z. Okay? So we broke it into 1 term and 2 term. And pay attention that the integral is just going to sum over z. So we are counting all possible z. So x and y are fixed. And z is going to be integrated. So we are adding all possibility. So what's the meaning of each term? So if you're going to have something like that, the first term, so imagine you're going to have 3 minus I lambda over 4 factorial of df of x minus y, integral d for z over df of z minus z, df of z minus z. So this is the propagator from point x to y. So imagine this is x, this is y. Propagator from x to y. Then you're going to have a point z, which is independent, which is separated. This z can be anywhere. This z can be here, 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 this z can be here. So all of these possible z. This is the meaning of this integral. But you're going to have the term propagator from z to z. This is the meaning of like some particle is just going back to itself. So we're going to talk about it in future more. So you have df of z times df z of z. Just notation wisely. So now, notation wisely, you're going to have this first term here plus the second possibility, this one. So now, what's the meaning of this? Is that you're going to have x here, you're going to have y here. So first you propagate from x to z, and then from y to z, and from z to z. So x to z, y to z, and then z to z. Okay? So these are all different kinematics that this field can happen. And I know that might be a little bit confusing, I think, for everyone. But the whole point is that this quantized field, they're not just continuous field. The expectation value of them can encode all of the possibilities of propagation from quantized point. Again, like in the second term, z can be here. So you're going to have something like from here to here and then to here. So these Feynman diagrams are just symbols that correspond to integrals. This is all it is. Okay, now if you want to summarize this whole session, what I can say is that if you have something like the expectation value on the perturbative vacuum time ordered of phi x, phi y, but the interacting Hamiltonian, this is equal to the perturbative vacuum time ordered of phi x, phi y, but in the interacting version or free fields. And then you have an exponential of minus I, the whole integral over time of the interacting Hamiltonian as a function of time. This is equal to sum of all possible diagrams with two external points. These diagrams, they have several ingredients. First, you have external lines, you have internal lines, and then you have the vertices. Each of them represents certain things. So external lines are representing real particles or something that it is incoming or outgoing. For example, if you have so you have incoming electron, and then you have so incoming electron is similar to an outgoing positron or any kind of particles, and then you have, so this is incoming, and then you have outgoing particles. Okay, these represents real particles. They are something that externally exists. The quantum number is there since the beginning. It's not a kind of virtual particle. Okay, so internal lines, they represent propagators. So these propagators, they correspond to virtual particles. So these virtual particles, they can be force carriers between real particles. Okay, and then you have vertices. These vertices are basically x and y. So these vertices, sometimes you also have z, as we said, all the possible diagrams. So you can have external points. These external points or external vertices is where the real particles are incoming and outgoing. And then you also have vertices in between. So this could represent virtual self-propagating particles. But these vertices, they are interchanging point that represents the coupling. So these are interchanging points that represents the coupling strength. We would talk about these more. In general, these Feynman diagrams have these ingredients: external lines, internal lines, and a number of vertices. These number of vertices, two of them, we basically said two external points. Two of them represents the interchanging point of the real particles. For example, you have an incoming electron, an outgoing electron, and then they exchange a photon. This is probably the very famous Feynman diagram, electron-electron scattering. So these are external lines. They represent real particles. They're there. Then you have a virtual particle here. A photon is a virtual particle. And then you have these vertex. These vertex they are the point that these virtual particles and these real particles, they intercept. And then this represents a coupling. A coupling is basically representing the strength of interaction. So each Feynman diagram is built out of these propagators, vertices, and external points. Now we can talk about Feynman rules. So these Feynman rules are basically telling us that how each diagram defines the integral. So we can have different types of diagram, as we said, all possible forms of diagrams with so many possibilities, so many vertices. But we want to see how each diagram encodes these integrals. So these Feynman rules, they can express in two forms, in the form of a space-time format, and then also in the form of momentum. As we know, space-time and momentum are interconnected by the Fourier transformation. So first of all, let's talk about the Feynman rules in the space-time, and then we can go to the momentum space, which in fact momentum space is more practical in terms of how it is useful, because we don't usually use a space-time really as a measure of the interaction of the strand. Mostly we're talking about the momentum of the exchange particles. So the Feynman diagrams are saying that if we have a propagator between x and y, so this x and y are basically those fixed points between the two. X and y are fixed points. So a propagator is something that propagates from x to y. This corresponds to a Feynman propagator. Feynman propagator is an expectation value of the integral. So a propagator is just Feynman propagator. Then you have vertex. A vertex is something, for example, in the phi-4 theory. So these are explicitly talking about phi-4 theory. A vertex is something that has 4 external lines or 4 external particles coming to this. These correspond to the coupling constant. So this lambda is the coupling constant. And this is how each vertex shows it is related to a coupling. So if you have so many vertex, then you have a lot of coupling. And each coupling is proportional to the constant that the theory is representing. So here we said the Lagrangian of the interaction, or the Hamiltonian of interaction, is minus I lambda over 4 factorial of phi-4. This is a coupling constant. So this coupling constant is beyond the integral, and then you have an integral d4 of z for that particular vertex. So this is an arbitrary vertex, not an external vertex. Then you have external point. So external point is something like x, and then you have a particle. This corresponds to 1. You don't have to do anything for that. And then the fourth ingredient is to divide to the symmetry factor. What it is for is to overcome overcounting. So you're gonna count all the possible scenarios, but many of them are equivalent to each other, so you don't have to count all of them. So you have to calculate the symmetry factor, how many possibilities is that, and then you divide it so you're avoiding overcounting. Okay, now we want to express the Feynman rules on the momentum space, but before starting to extract how does the Feynman rule are expressed in the momentum space, we have to talk about the philosophy of why we mostly want the momentum space instead of space-time, because it's more convenient. So I'm going to write down the question, why momentum space? There are several reasons. Again, the Feynman diagrams are integrals that they provide a basis to calculate the amplitude, the probability amplitude that we usually show with m. And this m is a function of, for example, how many vertex we have. For example, x1, x2, x3, and x4. And basically, when we are expressing those amplitude in the momentum space, we are having less number of independent variables. So each of these, like momentum, each of these two pairs of the points, for example, here, m of x minus 1 is translated into some m tilde of p. And that means that we are reducing basically the effective number of independent variables, which mathematically is more simple or simpler. The other reason is in particle physics, in the detectors, imagine this is the detector, and something happens here. Imagine a heavy ion collision happens, or some collision happens that we are interested. And this is the fireball, and the outcoming particles, they're just coming here. But usually we have a lack of precision really to measure the distance between x and y. I mean, imagine these distances are extremely small that our devices are not able to really measure those distances. But it is convenient to measure the momentum of the particles. So our detectors are basically capable of measuring the momentum of the particles, not the exact points that they're coming out. And again, if you think about it, it's not really important that whether it's x and y or where are they located. They can be anywhere, and there's so many other possibilities. What's important for you is that kinematic variable is the momentum that is carried by the propagator, or the momentum of the final particles, or the basic kinematic observable that we really care about. So that is because of the experimental restrictions that we have, that we cannot really measure the exact locations of those interactions, but instead we are just measuring the final state momentum of the particle. And the other reason is, so in the mathematical analysis of the Feynman diagrams, the green functions is calculated from the integration of, let's say, imagine I have g of x and y. This is calculated from the integral of d4 of z. Imagine z is another point, and you have several functions here. You have x minus z, and then you have the potential of z, and then you have another function from y minus z. And this is computationally very hard to calculate this integral, because we wanted to calculate these green functions. These green functions are propagators. But when we are turning into the momentum space, and you're dealing with g of p, this is proportional to the Fourier transformation of those functions times v, and then Fourier transformation of p. And basically reducing the integral into the linear summation of simple algebraic multiplication. So I can say in Fourier transformation, you simplify your equation by just summing linear terms, and you know how to deal with them, and then by knowing them individually, you can try to sum them up. So mathematically, there are many reasons why we prefer momentum space instead of a space-time. So now if you go to the Feynman rules in the space-time, for example, each of the propagators, for example, between x and y, as we said, is equal to a Feynman propagator between x and y. And if you remember, df of x minus y is equal to the integral over d4 of p, 2 pi over 3. And then you got this term here, p squared minus m squared plus I epsilon, to avoid the poles, exponential of minus I p dot x minus y. And now if you look at this term here, this term is a term that we would call it probably d tilde of f of p, because this is the Fourier component of this function. And of course, there is a weight factor, exponential weight factor, and then you have this conventional term for normalization. So this is the amplitude that we care about, proportional to the amplitude as a function of momentum. And basically, the direction of the momentum is up to us. We can put it from here, from left to right, or you can put it from right to left. But now we have to choose a convention to say if x0 is larger than y0, that means something is propagating from y0 to x0. So usually the particle goes from y0 to the x0. This is similar to the current in the circuit. So if you think about the current in the circuits, it doesn't matter what direction we are thinking about. Usually the electrons are going, imagine, in this way. But what you say is that I want to put my current direction as the flux of the positive charges. And there is no positive charges here, but again, it is completely arbitrary to choose which one is that. The other important thing is vertex. Now for each vertex, so any d of x minus y is replaced by, maybe I would say, df of p, which is proportional to 1 over p squared minus m plus I epsilon. So this is the factor that we care about each of the momentum mode. And again, we have to sum over all possible momentums. But this is like a linear sum. Okay, so that was the first one. The second transformation is the vertex. So the Feynman rule was for each vertex in the phi-4 theorem was that there was a point z, and then there was this phi-4 factor, right? So there was 4 particles into one vertex. And then anytime we see that, we said we're gonna replace it by minus I lambda, and this lambda was a coupling. And again, it's important to know, if we have more vertex, these lambdas are going to be repeated more and more, and then you're going to have minus I lambda to the power of n. And if lambda is very smaller than 1, or if we really have a perturbative theory, then these terms are going to go to 0. So minus I lambda to the power of n basically eventually approaches to 0, and that basically reduces the contribution of the possibilities that they have so many vertex here. So that's why we only care about the first few orders of those Feynman diagrams, usually first or second orders, because as you go to the higher and higher orders, you're going to have more vertices, and these vertices, each of them are proportional to a certain coupling constant. If the coupling constant is perturbative, as we see in quantum electrodynamic, those contribution goes to 0. But this is not the case, for example, for the case of QCD. So QCD, so you have QED. QED is a perfect theory. It's a perturbative theory, and it's working very well. QCD usually have a perturbative part and also have non-perturbative part. So the perturbative parts happen when the energy is really high, and when the energy is high, everything is perfectly similar to QED, and again, the number of vertices is proportional to the coupling constant, but the coupling constant is a small and perturbative section. But when you approach the energies around usually 100 MeV or even more, it depends on the number of flavor do you have, this approach doesn't work anymore. So Feynman diagrams are not useful anymore, and you cannot really calculate the amplitude of a scattering. So QCD is somehow a theory that has a dual behavior. So we have some well behavior that we can calculate the amplitudes on a very early stage of a collision, very high energy scattering jets and those high energy particles, and then non-perturbative part, which is actually the part that confinement happens in that energy. So confinement is when quarks and gluons, they are combined in the units that are called hadrons, and they cannot leak out anymore. This is called the non-perturbative section of QCD, and it's basically a very ongoing subject of investigation. How can we understand it? What effective theories can explain non-perturbative QCD, and what numerical approach we can have? But at this point, I just want to let you know that sometimes, as far as the theory is perturbative, these Feynman diagrams can work well because the number of vertices is proportional to the coupling constant. So coupling constant should be small to be perturbative. So now let's just talk about phi-4 theory. So in phi-4 theory, you have, again, like one vertex, and then you have 1 phi, 1 phi, 1 phi, 1 phi. Now, if you want to transfer that into the momentum space, you had minus I lambda, the integral of d4z. Now I'm going to show you how in the Fourier space this indicates the momentum conservation, because that basically tells you that anything that goes into one vertex or anything that comes out of one vertex is somehow should be related to momentum conservation. And the momentum conservation, how the momentum conservation can be driven out from the Fourier transformation. So in the phi-4 theory, the potential or the interaction Hamiltonian is proportional to the integration over all points of a space, and then you have phi of x to the power of 4, right? So if we decompose any phi of x into the Fourier mode, you have an integral over d4 of k. Let's say I'm taking this as k, and then 2 pi over 4. And then you have exponential of I k dot x phi tilde of k d phi k, right? This is the decomposition. Now, the integral, now the potential, if we want to express the potential in the momentum space, is going to be proportional to d4 of x. Now you have the power of 4 of this integral, right? So you multiply this integral 4 times. So I can basically write it down as the symbol of multiplication. So I from 1 to 4. And then I have d4 of k. Now I'm going to put this index I. This index I is just representing, these k's are not the same. Each of them represents an integral over 2 pi 4. And then you have e to the power of I ki dot x phi tilde of ki. Okay? It's just basically rewriting the potential if we decompose that phi into the Fourier mode. Now, because integral is now a linear operation, this is going to be the multiplication of I from 1 to 4, and then I have the integral of d4 ki 2 pi 4 phi of ki. It doesn't have any independence. And then I have the integral of d4x, and then I have the exponential term e to the power of I. Now I have k1 plus k2 plus k3 plus k4 dot x. Sorry, this phi has a tilde on top of that. So now what? the Fourier mode of this integral is this part of the function. Now, if you integrate it over d4 of x to just transform it into the momentum space, this is equal to 2 pi 4 delta of k1 plus k2 plus k3 plus k4. So you're going to have a potential. So your potential is proportional to the multiplication of d4 ki 2 pi 4. 2 pi 4 cancels the 2 pi 4. So I don't have to write it down. Then I'm going to have phi tilde of ki. And then I'm going to have delta of k1 plus k2 plus k3 plus k4. And it's just interesting, because that is momentum conservation for each vertex. So it is up to us that how do we want to draw the arrow of those momentum. The first possibility is that there are 3 momentum goes in, P1, P2, P3, and then 1 comes out, P4. So you're going to have delta of P1 plus P2 plus P3 minus P4. Then your momentum conservation form is going to be like that. So that basically means 3 annihilations, and then 1 production. The other possibility is that you say, I'm going to consider 2 particles comes in and 2 goes out. That can be called elastic scattering. Means 2 by 2. 2 goes into a vertex and then 2 goes out. So the nature, the number of particles doesn't change. The number of particles that goes in doesn't change. So 2 particle goes in, 2 particle goes out. So it's just elastic. It's just about the exchange of the momentum. So just P1 and P2 goes to P3 and P4. And if you pay attention, it's very different from the first one. In the first one, you get 3 particles goes in and then 1 particle comes out. And basically the number of particles are now changing. 3, for example, 3 particles of the same type went in and then 1 particles are coming out. So it is not called elastic scattering. It's inelastic because you're changing basically the degrees of freedom. But the second one is different. The second one is 2 by 2. And then you also have the last possibility is that just 1 comes into vertex. So let's say P1. Oh, sorry. For the previous one, you have to express it in the delta of P1 plus P2 minus P3 minus P4. So you can see just changing of the convention is just changing the possibility of how do you look at it from the physical process. So you can see it is up to you how to consider the arrow of the momentum inside of the vertex. But if you consider different possibilities, that would express the different physical processes. So 3 annihilations, 1 production is inelastic scattering. And then you have elastic scattering, 2 in, 2 out. And then you have 1 in and 3 out. 3, P1, P2, P3, and P4. And what is the meaning of that? It's a decay. So 1 just break into 3. That's a kind of decay for the 5 processes. So in that case, P1 minus P3 minus P2 minus P4. So that is the meaning of the momentum conservation. And momentum conservation, again, is followed by the mathematics of the Fourier transformation. And that's why the Feynman rules in the momentum space have to consider the momentum conservation. Any set of momentum that we are thinking about going into one vertex should balance each other in the way that they don't violate the momentum conservation law. So now let's summarize the Feynman rule in the momentum space. Feynman rules for momentum space. So for each propagator, from x to 1, we're going to replace it with I over p squared minus m squared plus I epsilon. For each vertex, you have to draw the arrow of the momentum lines, and that is proportional to minus I lambda, and then instead of the integral, I'm just going to put the delta of P1 plus P2 plus P3 plus P4. So that comes with the third law, which is the momentum conservation. For each vertex. Now for each external point, so in this, if you remember in a space time, each of these external point, they don't correspond to an integral. So there is only a coefficient of 1. So if you're confused, what was that 1? It means that for any external point, you don't have an integral. So you just put 1. Now, if you take it to the Fourier space, then you have a factor of exponential of minus ip dot x. So you are considering that in each point, there is an ingoing momentum, and that ingoing momentum is giving the scale factor of exponential to that particular point. And then, so this is the fourth, and then fifth is the divide by symmetry factor. So these are the Feynman rules for the momentum space. They're just directly taken from the space Feynman rules, and then you can calculate the amplitude as a function of different variables. And these amplitudes are going to be used in calculating the cross-section. We're going to talk about the S matrix and cross-section and the meaning of those processes, but it was all for a very simple theory, and that theory was the phi-4 theory. Let's say gamma over 4 factorial phi theory. And this particular theory has these vertex forms, and these vertex forms are giving us particular forms of momentum conservation. And now we're going to see in a realistic situation, when you have QED, you have fermions, and then you have bosons, these Feynman rules are going to be modified slightly to give us the way to calculate those probability amplitudes. So these probability amplitudes, they can be expressed in form of x1 to x2 to xn. It depends how many external points we have, or we can express them in a form of p1 up to pn, or how many external particles with momentum we have. So again, like a Feynman diagram, you can look at it in two ways. The first way is that there is fixed points. You have processes that they start at x and they finish at y, and there's so many possibilities. Imagine the simplest one is this. And then you have more complicated forms of them. And then you're summing all of them together. But the whole point is that your degrees of freedom are the endpoints of this interaction, right? Or you can express it in the momentum space. So you don't really care about where do they start or where do they finish. All you care about is that there is some ingoing momentum, and then you have a propagator momentum, and then you have outgoing, let's say, momentum. So instead of having two fixed points, you have momentum. And now if you think, oh, I have 5 momentum here, I only have 2 degrees of freedom. Now why do I have P1, P2, P3, P4, and P5? You need to consider that each vertex imposes the momentum conservation. So here you have P3 minus P5, P4. Sorry, P3 and P4 in this case should have the same signature because they're ingoing into vertex, and then P5 is coming out. So for this case, for example, I should have delta of P1 minus P3 minus P2, because P1 is going in and then P2 and P3 are coming out. So it is more convenient to be in the momentum space instead of a space-time, because again, like, you can't really measure those distances, but what you can measure in your detector is the momentum of your outgoing or ingoing particle. This is something that you can measure. And again, like, each 2 points can reduce into 1 momentum. And that's, again, like another mathematical convenience. Like, you're taking 2 into 1, and you're making your calculations easier. Now let's go back to the original problem. The original problem was saying that the expectation value of phi of x, phi of y is equal to the limit of time goes to infinity of some numerator and denominator. So the numerator was expectation value on the ordinary vacuum, time order operator, phi x I, phi y I, and then you have exponential of some minus t to plus t, and you also have the space coordinates, so d4 of z of h int of z, okay? And then on the denominator you have the only exponential function. And again, this is very similar to the partition function calculation in statistical mechanics. And then we discussed that how the expression in the denominator can be calculated using these Feynman rules. Now, one of the questions was what is happening when we also have this normalization, and how basically what we have in the denominator is going to cancel out something of its own form in the denominator. So the question is, can we separate this exponential here from the rest of these fields and somehow create an argument similar to that, and then you can cancel out these two parts. So that's the goal. That's the ultimate goal. So denominator is going to be sum over all possible diagrams. And then you have the value of integral. So imagine I say any value of the integral has some index I, and then you are summing I over all possible diagrams, and then you're summing the value of the integral of that diagram. This is equal to sum over all connected diagrams, which basically means anything that it is connected from x to y. So in the first order, x to y is connected directly, and then you have x, and then you have a bubble here, and then you're connected to y. And then you also have a situation when there are 2 points in between. And then all the other terms. So these are all called connected diagrams. So we have all sums over connected diagrams, which means that all the contraction between x and one of the component of the exponential, and then somehow ultimately 2 by 2, they connect back to y. So all the connected diagrams. And then you have sum over all disconnected diagrams. So what does it mean? It means that now any of these connected diagrams are there. In the background, you can have bubbles in vacuum. So imagine this is vacuum, this is vacuum, and then this is completely in the independent space, and then you can have some bubbles here. You know, I would call it Z, or these bubbles can be higher orders, so you can have 3 bubbles like that. You can have bubbles like this. So imagine, so this is imagine X, Z, W, this is Z, W, these scenarios, or you might have X, W, and U, and all the possible scenarios that the vacuum can bubble out this 5-4 theory. So these are 5-4 background. Because these two are independent from each other, so you have all connected, and then you have all disconnected. Now, let me invent a notation. I would say V of I is the value of integral that belongs to each of these forms of bubble. So imagine this is the first form. Then you might have 2 points here, and then you might have, you might have 2 points here. You might still have 2 points, but you might have a different forms of connection. And anytime you're adding something new, you get more complicated diagrams. But the whole point is that anytime that you have these vertices, then the coupling constant would take the probability of these value lowers in the integral. So imagine V of I represent each of the integral value of these bubbles. Imagine I'm denoting them with I. Now imagine each of these bubbles have a symmetry factor Ni, and this Ni is just showing that how many ways you can overcount them, or how many ways that you can do the permutation of the index, so they are distinguished, and then you overcount them. So this is going to be, so the expression above is going to be sum over all possible diagrams is going to be sum over all connected diagrams, and the value of
connected diagrams. Now sum over all combination of ni factorial. So all combination, sum over all possible ni ways that you can order them. For example, n1, n2, n3, and n4. So this is the first bubble, second bubble, third bubble. So this is something happening here, something happening here, something happening here. So this is called an ni set. So now you're summing over all possible ni, I mean all possible configuration or all possible ways that these bubbles can exist. So you're summing over all ni, then you have the multiplication over index I of 1 over n I factorial, and then you have vi to the power of n I. So again, let me, if I want to say how, why does it look like that? So that means all possible ways for bubbles to configure. So it's a set of numbers, for example, ni to np. And then you might have another set, n prime r1 to n prime p. So we are summing over all possible ways that these bubbles can arrange themselves. Then each of these bubbles have a vi. So this is a value of bubble integral. But it happens ni times because you can do the permutation ni times. Their symmetry factor is ni. So you have ni independent of those events that can happen. So you can multiply all of them. So this is vi to the power of ni. And then in order to avoid overcounting, you have to normalize it to ni factorial, right? And now this is where you can separate this expression here. So this is equal to sum of all connected. Then I have, imagine I have sum over all n1. And then I have all n1 factorial v1 to the power of n1. So imagine n1 is a set of bubbles. And then I have multiplied to n2, and then 1 over n2 v2 to the power of n2. And so on. So this is going to be sum over all connected times the multiplication over index I of all ni 1 over ni factorial v of I to the power of ni. And this is going to be exponential of vi. And then I'm going to have sum of all connected piece, and then I have the multiplication of exponential of each vi, which is now going to be sum over all connected piece. And then now this is going to be exponential of the sum of vi. So this, I can show it as exponential of each of these vi's. So for example, that plus that plus that, and so on. So my formula is going to be, so this expectation value is going to be sum of all connected diagrams times exponential of the sum of all of these bubble integrals. And in the denominator, this is also going to be equal to this expression. So this, based on the Wick's theorem, is all the contraction between the exponent of the exponential, which are basically independent bubbles. So this is also going to be exponential of the sum of each of these vi's, or this expression in the numerator and denominators are going to cancel each other out. So our expression is going to be only the sum of the value of the connected diagrams. which means only sum the connected diagrams from x to y plus x to y, and then you have z here and the other terms. So we don't have to be worried about the normalization factor in the denominator because you can take it out from denominator points based on this way that we separated connected piece from the independent bubble that are disconnected, and basically just showing that the expectation value is equal to only the sum of the connected diagrams. So that's the end of this session. So that was the Feynman rules for the 5-4 theory. That was a scalar theory, very simple theory. In the next session, we are going to talk about the application of Feynman diagrams in quantum electrodynamics, and we're going to bring in the fermionic fields and the bosonic field together in order to calculate real Feynman diagrams between the fermion and boson exchange, something that we see in quantum electrodynamics. The electron-electron interaction, and then the photon exchange and electron-electron out, or you might see some even correction to that. So you might have some radiation here on one of the legs and so on. So we will learn how to calculate all of those pieces. But the summary of this session is going to be how each of these diagrams represents an integral. An integral has a value, and then the way that you should arrange these values are using this Wick's theorem. So I'm going to review this session one more time. So at the beginning, we talked about this Wick's theorem. Wick's theorem is using the properties of the field when they are free in order to normal order them. So we learned what's the connection of the time ordering and normal ordering, and then normal ordering and the contraction. So we can have all possible contraction. That was the Wick's theorem. So we were able to basically do 2x2 calculation, and 2x2 calculations are propagators, Feynman propagators. So we could express all of those terms based on Feynman propagators. And then we have the expectation value that we want to calculate for the 2-point correlators or 2-point correlation function. And we use Wick's theorem in order to 2x2 contract these diagrams, and basically taking out those visual part out of them. So how Feynman diagrams represents these 2x2 contractions, and each of these 2x2 contractions are a Feynman propagator. It's a Feynman integral. And then we express the Feynman rule in the space-time coordinate, how we are treating the external lines, internal lines, and vertices. And then we also express the Feynman rules in the momentum space, which was more convenient. This is something that we have experimental access to the momentum of the particles, and we want to express these Feynman rules in the momentum space and integrate over momentum. And we showed how this Fourier transformation is leading into the momentum conservation in the Feynman diagram. So you can have different types of processes, separate interpretation from the same kind of vertex. So you can have 3 annihilation, 1 production, then you have 2x2 elastic scattering, and then you have a decay, that 1 particle decays into 3 particles. And then we also ultimately address the problem of the numerator and denominator normalization, and we concluded that the denominator represents independent bubbles, and independent bubbles have the sum of all possible configurations that these bubbles can be created, and then we somehow factorize them from the connected pieces, and then using the symmetry factor of all of those bubbles, we cancel out the numerator and denominator, and then we conclude that the 2-point correlation is only the sum of the connected diagrams. That's a very beautiful identity, and I'm very happy that we are here. So we will see you in the next session. Thank you so much.